Okay, hello everyone. In this lecture series, we are discussing variational principle or variational method. That is, expectation value of Hamiltonian by considering any state of a system is always greater than equal to eigenvalue of ground state. Already we have been proved this uh, by this one by help of a theorem. This variational method or principle specially used to find out the ground state energy of a system. Also, it can be useful to find the excited states of the system that we are going to discuss later. Last class we discussed this question. Use the variational principle to evaluate the ground state energy of 1D linear harmonic oscillator. Here trial wave function given c to the minus ax square. To solve this question, we followed this procedure, 4 steps. First, we have to write the Hamiltonian of the system, then consider a trial wave function psi, then normalize it. If in the question it is given, then no problem. If it not given, then we have to construct the trial wave function. Then third step is your calculate the expectation of Hamiltonian by considering any state function of that particular system. Then apply the minimization condition on the expected value of Hamiltonian. Okay, so these are the steps that we have to follow to solve a problem. In today's class, we are going to discuss this one. Question number 2. Use the variational principle to estimate ground state energy of hydrogen atom using trial wave function c e to the power minus ar, where a is a parameter and c is the normalization constant. Here normalization constant given, it is not normalized. That means we have to normalize this wave function. Okay, so we have to follow these steps and we have to solve this question, or we have to find out the ground state energy of hydrogen atom. Okay, so let us start. Here in this question, already trial wave function given c e to the minus ar. Okay, now first step to write the Hamiltonian of the system. The Hamiltonian of the system is this one, minus h cross square by 2m del square minus 1 by 4 pi epsilon 0 z e square by r. This is for hydrogen like atom. For hydrogen, z will be 1. Okay, so here so you just consider this one is your hydrogen atom. This is the nucleus. Okay, one electron somewhere in 1s orbital. Ground state means spherical symmetrical. Okay, somewhere in 1s orbital. So we have to consider a spherical symmetric construction of a hydrogen atom. That is your 3D spherical symmetric that we have to imagine in our mind. Okay, now the Hamiltonian for hydrogen atom will be minus h cross square by 2m del square minus 1 by 4 pi epsilon 0. Here z value is your 1, so e square by r. This part is your kinetic energy part. This part is your potential energy. Potential energy. May you remember last class we have been discussed. This is the kinetic energy part. See, p square by 2m or minus h cross square by 2m del square by del x square. For one dimensional, del square by del x square. For 3 dimension, if we are going to consider, it will be del square by del x square plus del square by del y square plus del square by del z square, or simply we can write del square. Same thing it has been written, minus h cross square by 2m del square. Okay, this is the Laplace operator also you can say. Next, second part is the potential energy part. Here potential energy in between nuclear charge and this electron. Suppose if we are going to consider hydrogen like atom, like helium plus lithium plus, that means helium 1 electron given to someone, lithium lost 2 electrons, so lithium plus, helium lost 1 electron, so helium plus. So if we are going to consider helium plus or lithium, suppose lithium plus, then this z value will be equal to 3. If we are going to consider helium, then this z value is your 2. But in this case, z value will be 1 because we are considering hydrogen atom. Here I written Hamiltonian for hydrogen like atom. Why? because in general, suppose in your question it is given that to find out ground state energy of a hydrogen like atom, then you have to follow this Hamiltonian. Okay, and that time when it will ask for hydrogen like atom, here psi will be written. You can see uh, in that question it will be asked psi will be e to the minus ZAR. Okay, minus ZAR. Trial wave function will be given this one for hydrogen like atom. Okay, now this Hamiltonian will be written as minus h cot square by 2m del square minus here 1 by 4 pi epsilon 0 can be written as k. Okay, k z e square by r, or if we are going to consider hydrogen atom, then this value is your 1, so k e square by r. Okay, okay. So here our Hamiltonian of this system of this hydrogen atom, we written this one, equation number 1. Okay, why it is minus? Why it is minus? Because both are repulsive. Both are attractive. Both are attractive. Z, nucleus and electron, attractive. So obviously potential energy will be written in the form of negative. May you remember this graph. Attractive potential energy always negative, so it is negative. So potential energy here 1 by 4 pi epsilon 0, or you can write instead of 1 by 4 pi epsilon 0 you can write k. Okay, now we are going to go for normalization of trial wave function. See, trial wave function for this system is given this one. C is the normalization constant, it is not normalized. So our second step is that if trial wave function given and not normalized, then first we have to normalize it. So you just normalize the trial wave function by considering the normalization condition. This is the trial wave function. C is the normalization constant. Inner product should be 1. So here 3-dimensional case we are going to consider, because this is the 3D spherical symmetry case. Hence triple integration will be come up. Okay, but in case of 1D harmonic oscillator, what we discussed in our last class, only single integration, because along x-axis dynamics was there. But in hydrogen atom, 3-dimensional sphere means we have to consider triple integration. So triple integration, inner product of trial wave function should be 1. This is the condition, normalization condition. So here C is the constant. So C star will be C mod square taken outside, triple integration. Here e to the minus AR into e to the minus AR. So it will be e to the power minus 2AR dQR equal to 1, right? Now, as it is spherical symmetric, that we consider it is spherical symmetric, then this integration, the 3 integrations will be R with respect to R, with respect to theta, and with respect to phi, that we know in case of 3D or 3-dimensional spherical symmetric case. So C mod square, and here see dqr is nothing but, here in case of 3-dimensional case, dqr, this is the small volume element, is nothing but r square dr sin theta d theta d phi. Okay, so here dqr is the function of r, theta, phi. So the 3 integrations will be integrated separately for r, theta and phi. Here segregatedly it has been written for r. So here r square dr, r square, this is the function of r, e to the power 2AR dr, then sin theta d theta, and for sin theta d theta it will be integrated from 0 to pi. For r the limit will be 0 to infinity. This is the basic of a 3-dimensional sphere, and for d phi integration will be 0 to 2 pi. Okay, now simply if you are going to integrate sin theta d theta, sin theta d theta 0 to pi, it will be 2. Okay, you just do it in your rough. Sin theta means integration will be minus cos theta, a limit is your 0 to pi, so minus cos pi minus cos 0. Okay, so cos pi is your minus 1, this is cos 0 is 1, so it is minus 1, So finally this minus, this is minus 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 to 2. So sin theta d theta integration 0 to pi, you just remember 2, and d phi integration with limit 0 to 2 pi will be 2 pi. This integration value will be 2 pi. So this double integration value is 4 pi. You just remember this one. In our next class, whenever we are going to face this type of integration, directly I am going to substitute this two integration, theta integration sin theta d theta into d phi integration will be 4 pi. Directly I am going to put. Okay, so here I explained how it is 2 and how it is 2 pi. Now for this one it is written as 2, for this one it is written as 2 pi, so it will be 4 pi. Now this integration value will be this one, 1 by 1, this one 1 by 2a to the power 3 gamma 3. Why? Already we know 0 to infinity x to the power n into e to the power minus a x to the power m dx. This is the gamma function integration, is nothing but 1 by m into 1 by a to the power n plus 1 by m gamma n plus 1 by m. Just compare this integration and this integration. Limits upper and lower are same. Here instead of x, r is there, and dx and dr is there. So here n is nothing but 2, here n is nothing but 2, and a here a is nothing but 2a, and r to the power 1, here m is nothing but 1. So here m is 1, a is nothing but your 2a, and n is your 2. So what will be its value? 1 by m, 1, into 1 by a is nothing but 2a, to the power n plus 1, n is 2, 2 plus 1, 2 plus 1 is your 3, by m is nothing but 1, okay, into gamma 2 plus 1 by 1 is nothing but 3. Same thing it has been written, 1 by 1, 1 by 2a to the power 3 gamma 3. So here 1 by 1 1, 1 by 2a to the power 3 it has been written. Gamma 3 is nothing but 2 factorial, that we know, because gamma n plus 1 equal to n gamma n, or n gamma n is nothing but n minus 1 factorial. Okay, so here gamma 3 is nothing but 2 factorial. Okay, this is the basic property of gamma function. So here we found the c value. Just you calculate these two steps, you can get c value equal to a q by pi to the power 1 by 2. Here you can see here 2 factorial means 2, so c mod square, this is 2 to the power 3, here 2, and this is also 2 to the power 3, 2 to the 3, 2 to the 3 got cancel, and we found pi by aq equal to 1. So c equal to aq by pi to the power 1 by 2. Okay, here one thing you have to remember, for hydrogen like atom, suppose it will be asked, the c value will be zq to aq by pi to the power 1 by 2. Same calculation if we are going to do for hydrogen like atom, by considering wave function is your psi equal to c to the minus ZAR, then finally you can get this one. Why I am telling about the hydrogen like atom? Because in our forthcoming classes we are going to discuss about helium atom. We are going to discuss the finding the ground state energy of helium atom. At that time this expression is required. So you just remember, for hydrogen, no need, if you want you can do separately in your note, but here same procedure if you just follow, then this ZQ term will be come up extra. ZQ AQ, here AQ is there, by pi to the power 1 by 2. Okay. Now the corresponding normalized wave function will be how much? Here c value we got this one, so corresponding wave function psi will be equal to, instead of c we have to write aq by pi to the power 1 by 2 e to the power minus ar. Likewise for hydrogen like atom, the corresponding normalized wave function will be zq aq by pi to the power 1 by 2 into e to the power minus zar. You just remember these things. This one remember, I written in the bracket, you just remember. But if this question hydrogen atom asked, so no need to discuss about hydrogen like atom. Directly you have to write Hamiltonian is this one, and normalized of the hydrogen atom is this one, c value is this one. So no need to write these things. Okay, these things I written because in our forthcoming classes we are going to discuss about helium atom at that time it will be required. Now we are going to go for our third step. Third step is nothing but you calculate the expectation of Hamiltonian, right? Expectation value of Hamiltonian. Here heading I given expectation value of Hamiltonian for the state psi. Normalized psi value we got as equation number 2, right? So the expectation value of Hamiltonian of a system having a particular eigenstate psi in general written as angle bracket psi h cap psi, or integral form it can be written as integration of psi star h cap psi. In 3D it will be written as dqr by psi star psi dqr. But as this psi is normalized, so this value will be 1. So no need to write the denominator part. Only numerator part we have to write and we have to calculate. That implies expectation value of Hamiltonian will be equal to integration of psi star. Here h cap Hamiltonian, how much we found? This much. Same thing we have to write. Minus h cross square by 2m del square minus 1 by 4 pi epsilon 0 e square by r. Okay, same thing I have been written over there. This is the Hamiltonian, whatever written there. Psi dqr. Let this is your equation number 3. Now, here you can see if I am going to apply this one, see this term over psi, then we can get one term. Then this term whenever it will be apply over psi, another term. So first we have to calculate when del square or Laplacian operator, this is called the Laplacian operator, will be operated over psi, what will be the value? First we have to calculate, then we have to proceed, or we are going to simplify this equation number 3. First we have to calculate del square psi will be how much. Okay, here del square or Laplacian operator in spherical polar coordinate in general, it is written as 1 by r square d by dr of r square into d by dr plus 1 by r square sin theta d by d theta of sin theta del by del theta plus 1 by r square sin square theta del square by del phi square, operated over the given trial wave function c e to the power minus ar in the question. This one. Okay. Here the given wave function psi is the function of r only, but this del square operator is the function of r, here theta and phi. So whenever this factor will be operated over psi, the value will be 0, because here del by del theta is there, here del by del theta is there, but psi does not contain the theta part. So when this term will be applied or operated over psi r, we can get the 0. Likewise, if this term will be operated over psi r, also we can get the 0, because psi r have the only function of r, not phi. So these two terms when, or these two operators when operated over psi, we can found 0. Okay, now this factor, when this operator will be operated over psi, then what will the value? Okay, here that is calculated over here. See 1 by r square d by dr, r square d by dr. See here c e to the power minus ar, c constant taken outside, so this much operated over e to the power ar, sorry, e to the power minus ar, right? Now here you can see 1 by r square d by dr into r square d by dr is nothing but this much. How it is very simple. 1 by r square is there. Okay, d by dr of this one, just use the product formula, d by dr of r square d by dr. So first function, then derivative of the second function, d square by dr square. Then second function as such you just write derivative of first function, this is the 2r. Okay, so 1 by r square when multiplied with this term, we can get only d square by dr square, plus when 1 by r square multiplied with this one, r got cancelled and we can found 2 into 1 by r d by dr. Same thing it has been written here. See d square by dr square, d square by dr square, 2 by r d by dr operated over e to the power minus ar. If it will be operated over e to the minus ar, then the value will be this much. Next step, it has been written here. You can see the value will be this much. How and why? Here you can see c is the constant. So here the double derivative applied over e to the power minus ar, it will be minus a into e to the minus ar, right? Then plus 2 by r is there, then d by dr operated over e to the power minus ar. So this value will be a minus a into e to the minus ar, right? So here we found c into a minus a plus a square plus here this is minus is there, so minus 2a by r into whole into e to the minus ar. Same thing it has been written over here, right? So here c into e to the power minus ar is nothing but psi. So we found finally del square psi equal to a square minus 2a by r psi. Let this is your equation number 4. Now whenever if we are going to solve the equation number 3 by substituting this value directly, then our calculation will be very easy. Okay, now we are going to simplify the equation number 3, this one, equation number 3. Okay. So here we found Laplacian operator or del square psi in inverse spherical polar coordinate. For this trial wave function, we found this much, a square minus 2a by r psi. Let this is your equation number 4. Here same thing it has been written. Put 4 in equation number 3, we get equation number 4 will be substituted in equation number 3. That means del square psi value we have to substitute in the equation number 3. So here del square psi is nothing but this much value into psi. So psi again can be taken outside of this bracket in the equation number 3, outside of the bracket, and instead of del square psi we have to write this term, a square minus 2a by r. See, instead of this one we have to write this one, a square minus 2a by r psi taken outside of this bracket dqr. Got it? So here we can get the 3 terms. This one term we can get, then again this one and this one, 3 terms we can get. Now we are going to write separately. Here minus h cot square by 2m a square psi star already there. This much value is constant taken outside of this integration, psi integration, then psi star and psi star psi dqr. Got it? Now second term is this one, minus 2a by r minus h cot square by 2m. So here 2 got cancel, 2 got cancel, here 2 got cancel, and here minus is there, this is also minus, it will be plus h cot square a by m, h cot square a by m. R is the variable because integration with respect to r, so r will be inside the integration, so psi star 1 by r psi dqr. And the last term is your minus e square by 4 pi epsilon 0 is a constant taken outside of this integration, 1 by r should be inside the integration, so psi star 1 by r psi dqr. Got it? Okay. Now we are just simplifying in the next step. What we have to what we can found here, this value will be 1 because psi is a normalized wave function that we evaluated, so this integration value will be 1. So first term we have tried straight this value, minus h cot square a square by 2m. Okay. Then here you can see, if we are going to consider these two terms, this integration is common among these 2 terms, can be taken common from these 2 terms. So we can write, see, h cot square a by m, here I written, minus e square by 4 pi epsilon naught into this integral, right? That equal to same, this term written as such, Now we are going to integrate this one. Here spherical symmetric integration by considering 3-dimensional spherical symmetric spherical symmetric integration. So here, see, we have to substitute psi star value and psi value. Psi value normalized wave function value here. How much we found? A q by pi to the power 1 by 2 e to the power minus ar. A q by pi to the power 1 by 2 into e to the power minus ar. Psi star value also this much. Now here you can see psi star psi. When it will be multiplied, then this value will be aq by pi only. Aq by pi taken outside of this integration. Got it? Here 1 by r is there, 1 by r written. E to the power minus ar multiplied with psi r, that means another e to the power minus ar will be come up. So it will be e to the minus 2ar. Here I written e to the minus 2ar. Right? Then dqr volume element, that we know what, r square dr sin theta d theta and d phi. Right? So r square dr is the function of r, that means integration, this will be integration with respect to r. So here 1 by r e to the power minus a by r, also function of r, and r square dr, this is one integration, and this limit will be 0 to infinity, right? 0 to infinity. And second integration will be sin theta d theta, and the integration limit will be 0 to pi, that we know, and phi d phi, integration limit 0 to 2 pi. And these two integration value is nothing but 4 pi, just we have been discussed above. Okay, 4 pi, or this value is 2 and this value is 2 pi, so obviously it will be 4 pi. Okay, in the next step, same thing, this term written as such, this term written as such, aq by pi, here it is written aq by pi 0 to infinity. Here r 1r got cancelled, we can found r e to the power minus 2ar dr. Right? In the next step, same, this term written as such, here 2 into 2 pi, 4 pi taken outside of this integration, 4 pi aq by pi, and this integration value by considering gamma function, you can get this one. Already we have been discussed above. Here we discussed about how to use the gamma function. Okay, you just apply that one, very easy. Right? Now minus h square square by s, minus h square square a square 2 by 2m, as such it is written. Same, this term written here 4 pi aq by pi written. Okay, so this will be, they see gamma 2 is nothing but 1 factorial 1 by 2a square, right, is equal to minus h square by a minus h square a square by 2m. Here this term as such it is written here. This, after simplification this much, we can get a. How? Here you can see a square cancelled, pi cancelled, here 2 to the power 2 4 cancelled, only a will be remaining written here. Finally we found expectation value of Hamiltonian is this much, right? This is your equation number 5. So here we completed the major step of this question. This is the major step to calculate the expectation value of Hamiltonian. Okay. Now if we are going to consider hydrogen like atom, then what will be the expectation value of Hamiltonian? The expectation value of Hamiltonian will be, you just follow same procedure, you can check by your rough, same procedure you just follow, and you can find the expectation value of hydrogen like atom will be this one. Just one z square will be multiplied with this term, same term. See, h square a square by 2m, h square a square by 2m minus e square a square by 4 pi epsilon naught will be multiplied with z square for hydrogen like atom. Okay, you just keep this these things in your mind, because it will be required when we are going to discuss the helium atom, solving the helium atom. At that time it will be required. Okay, from equation number 5, here you can see, from equation number 5 it is found that expectation value of Hamiltonian is the function of the parameter a. Now we are going to follow the fourth step here. After completion of this step, we have to consider the fourth step. In the fourth step, what we have to do, we have to consider the minimum condition or apply the minimum condition on expectation value of Hamiltonian. So we have to apply the minimum condition on the equation number 5, that is differentiation of expectation value of Hamiltonian with respect to A, because it is the function of a parameter A and equate to 0. This is the method, or this is the way to minimization of a particular particular variable which is function of a parameter. Okay, so if I'm going to differentiate expectation value of Hamiltonian, this one here, with respect to A, first term will be h cos square by 2m is constant. A square will be how much? 2a. So 2 got cancelled. We can found h cos square a by m. H cos square a by m. Got it? Second term, here a is there. With respect to a, if I'm going to differentiate the value, we can found this much, e square by 4 pi epsilon naught. E square by 4 pi epsilon naught equating to 0. So that implies by simplifying this one, we can found a value is your how much? E square by m, e square m by 4 pi epsilon naught h cos square. Let this value equal to 1 by a naught. Let us this value we consider as 1 by a naught. So that implies a naught value will be how much? Just reverse 4 pi epsilon naught h cos square by e square m. This value is nothing but your Bohr's radius. You just remember or keep these things in your mind, because this term, Bohr's radius term, is very much essential for different numericals also. So here a naught is the Bohr's radius. Now we are going to substitute a value in equation number 5 to finding the expectation value of Hamiltonian at the minimum condition. So what will be the minimum expectation value of the Hamiltonian? If we are going to put this a value in equation number 5, then we can find what will be the upper bound or minimum expectation value of Hamiltonian. So you just substitute a value here. Here you can see here h cos square a square by 2m. A is here this much. So if I will put this one over here, so this will be h cos square by 2m. H cos square by 2m. Here it is written h cos square by 2m. Okay, so this will be here a square is there, no, a square is there, so it will be e to the power 4 m square by 4 pi epsilon naught square h cot 4, h cot to the power 4. Same thing it has been written, e to the power 4 m square by 4 pi epsilon naught square h cot to the power 4. Then in the second term, you just substitute a value. Already 4 pi epsilon naught present at the denominator. So if I am going to substitute this a value over here, then this value will be e square is there. Here e square, e to the power 4 will become, m is there, m, and the denominator will be 4 pi epsilon naught, 4 pi epsilon naught. So it will be 4 pi epsilon naught square, and h cot square is there. Sorry, here here h cot square is there, so h cot square, right? So here you can see h cot square by 2m. Here h cot square got cancelled. We found h cot square here. Okay, here m got cancelled. So how much we found? We found e to the power 4 into m. Here also e to the power 4 into m. 4 pi epsilon naught square, 4 pi epsilon naught square, h cot square. But this is the half value, this is the full value. So if we will subtract this one from this value, so we can found minus e to the power 4 by m by 2. This is a full value, so half will be remaining by 2 4 pi epsilon naught square h cot square. Okay, then that implies expectation value of Hamiltonian. So here this can be called as a minimum expectation value of Hamiltonian. Minimum expectation value of the Hamiltonian will be here e to the power 4m, e to the power 4m written as such. 2 here 4 square is 16 into 2 32 pi square epsilon naught square, here h cot square right? Here you can see h cot square is nothing but h by 2 pi. H cot square is how much? H by 2 pi. So this can be written as h square by 2 pi or 4 pi square, right? So here pi square will be got cancelled, 4 will be cancelled with 32, it will be 8. So we can found minus e to the power 4m by 8, 8 here epsilon naught square h square. You just substitute all the values. Here E is the charge. Charge is how much? Minus 1.6 in 10 to the minus 19. And m value, mass of the electron, 9.1 into 10 to the minus 31. And epsilon naught h value, you just put, and you can found the value will be minus 13.6 electron volt, which is exactly matched with the ground state energy of the hydrogen atom. Because in our modern physics we studied that nth state of the hydrogen atom, energy value of nth state of hydrogen atom expression is this one. In our modern physics already we have been studied, minus m e to the power 4 8 n square h square epsilon naught square. So if n equal to 1, I'm going to substitute over here. This value is nothing but this much. See here m minus m e to the 4, here minus m e to the 4, 8, here n value 1 means 1, 8 h square epsilon naught square, 8 h square epsilon naught square. So here exactly matched with the ground state energy of the hydrogen atom, whatever we found traditionally. Okay, so with the help of this variational method, or with the help of this trial wave function, or with this approximation method also, we found the same value. That means the method is correct, and the trial wave function whatever we have been considered, c e to the minus air, is the perfectly accepted wave function for the dynamics of the electron at the ground state. So ground state at the 1s state, if it will be in the dynamics, then that can be represented by this particular perfectly represented by this particular uh, eigen state or the wave function. And instead of c we have to write that value. The value is how much? A value, this one, c value, a q by pi to the power 1 by 2, a q by pi to the power 1 by 2 we have to write. Now here the equation number 6, this equation number 6, see if in your exam it will be asked you have to write up to this much, then equation number 6 can be written as rewritten in this format. Here equation number 6 means this one, I written over here. Here this can be written, this value can be written minus k e square by 2a naught. Here k value is nothing but 1 by 4 pi epsilon 0, and a naught value is this one, this much, 4 pi epsilon naught h cot square by e square m. You just do in a rough, you just substitute k value and substitute a naught value. Here you can found exactly this much. Why I written in this format? Because whenever we are going to solve, or whenever we are going to discuss about hydrogen like atom or about the helium atom, at that time it will be discussed in our forthcoming classes that we are going to discuss. So this type of expression, or in this type of format, we at that time we are going to use. You just keep this one in your mind. Okay, now this is the expectation value or ground state expectation value of Hamiltonian. We found this one or this one. If hydrogen like atom we are going to consider, the value will be only z square will be multiplied, z square, this is the atomic number square, z square minus k e square by 2a naught. Same thing, whatever this value, same value, only z square will be multiplied whenever we are going to consider the hydrogen like atom. So when we are going to discuss the helium atom in our forthcoming classes, when we are going to discuss about the helium atom, trying to find out the ground state energy of the helium atom, at that time we are going to use this one, this value. Okay, this value, this expression you just keep in your mind. Okay, now ground state wave function will be how much? Ground state wave function will be how much? We have to just substitute this a value. Here we have the normalized wave function is your how much? A q by pi to the power 1 by 2 e to the minus ar. Okay, a q by pi to the power 1 by 2 into e to the minus a r. Here we are going to substitute instead of a value 1 by a naught. 1 by a naught. So the ground state wave function will be 1 by pi already is there. Instead of a we have to substitute 1 by a naught, means this will be a naught q to the power 1 by 2 e to the power here e to the power minus a r. Instead of a we have to substitute 1 by a naught, so this will be e to the minus r by a naught. So this is the ground state wave function of the hydrogen atom. For hydrogen like atom, what it will be? It will be here zq will be come up. Here you can see about hydrogen like atom. For hydrogen like atom wave function, here we written. So instead of a we have to put 1 by a naught. So this will be zq by a naught q pi to the power 1 by 2 e to the power minus z r by a naught. Here I written. So I suggest that you just remember or keep in your mind this one, this expression and this expression. These two expressions are required whenever we are going to solve the hydrogen like atom, or when we are going to discuss the ground state energy of helium atom. Okay, so this is all about the solving of or to estimate the ground state energy of hydrogen atom for this particular question by considering this trial wave function. Now I am going to give you another question for your homework. I just changed same hydrogen atom, calculate the upper bound or ground state energy of hydrogen atom by using Gaussian trial wave function. This is another trial wave function. There in the question number 2 it was c to the minus ar. Okay, minus ar means like this type of wave function, but this is a Gaussian wave function. In this question, like this type of wave function, if we are going to consider, then what will be the ground state energy value of the hydrogen atom? You just do by yourself in your rough. You can do same procedure, same step you have to consider. Here I written the answers for your verification. Here I written the answers. Hamiltonian will be written as this one. Hamiltonian is not changed. Okay, k e square by r, or instead of k you can write 1 by 4 pi epsilon naught. And normalized trial wave function is given here. C value, after normalization C value you can found this one, 2 beta by pi to the power 3 by 2 C value. So normalized wave function you can found this one. Instead of C you have to write this one, e to the minus beta r square. Same, I left the space. Okay, I left the space for you that you have to do by yourself. Expectation value of Hamiltonian you can found this one, 3 h square beta by 2m minus k e square 2 root 2 into beta by pi root over. Expectation value you can found this one. And when you are going to apply the minimization condition to evaluate beta value, then you can found the beta value is your 8 by 9 pi a naught square. Okay, so here 8 pi 9 pi a naught value we know that h square by k is e square m, just we discussed previously. Here a naught is nothing but 4 pi epsilon naught h square by e square m, or this 4 pi epsilon naught can be written at the denominator, so this value will be k. So instead of 4 pi epsilon naught we can write k, no problem. So this value is your beta value. After substituting the beta value we can found expectation value of ground state energy is your how much, 8 by 3 pi into minus k e square by 2 a naught, or this one 8 by 3 pi minus e to the power 4 m by 32 pi square epsilon naught square h square. If we are going to substitute all the values, we can get the expectation value of ground state energy will be minus 11.56 electron volt. So if I am going to consider this wave function, Gaussian wave function, how much we found? 11.56 electron volt. But if I am going to consider the previous one, c e to the minus ar, we found minus 13.6 electron volt. That means here by considering Gaussian wave function, we are not approaching the exact value of the ground state energy. But when we are going to use this wave function, exponential decreasing, three dimensional, then we can approaching the. So which one is the better wave function, trial wave function, that we are going to consider finally? So this one c to the minus ar is the most appropriate or most approach wave function to find the ground state energy of the hydrogen atom. Okay, you do this question by yourself, I left for you. Here I am going to stop uh, today's discussion. In our next class we are going to discuss another interesting question. This one here first, here the previous three questions we discussed, that trial wave function already given in the question, trial wave function given. This question you just consider a particle of mass m that is bouncing on a reflecting hard floor. This picture, this is the ball, it is bouncing over this reflecting surface, and potential given is the mgx when x is greater than 0. So here along this side I considered x axis, so this floor is the reference line, so this is considered as x equal to 0. So above x equal to 0 the value is mgx potential, just x equal to 0 or below x equal to 0 the value is infinite, potential is infinite. That means this ball could not penetrate this surface, only bouncing over this surface. So here trial wave function is not given, trial wave function is required. So how to construct the trial wave function for this question, that we are going to discuss in our next class. Okay, so thank you so much for watching this video. Thank you.